Good evening, everyone. We're going to give it a minute to just let everybody go ahead and kind of get in for this session. Excited you could be with us tonight for Climate 101, the science and its implications for meteorology with Amber Liggett from NOAA in the Climate Program Office.
Thank you so much, John. Yeah, just let me know when it gets started.
Will do. Yeah, we'll give it a probably about a couple more seconds here just to let all the people that pile up in the waiting room come on in.
Okay.
All right, ladies and gentlemen, again, welcome to the webinar tonight. If you haven't attended before or you haven't seen any of the videos, I'm Dr. John Lohr with Science Olympiad in our national office. And I just want to go over a couple of quick housekeeping things before we get started with the content. First and foremost, this session is being recorded. You should have heard the announcement when you logged in that it's going to be recording. You will get a copy of the recording or access to a copy of the recording. That should happen hopefully sometime tomorrow for the cloud recording, and then later next week we'll get it posted to our YouTube channel. So you don't necessarily need to go into Zoom every time to see the video. Second, if you want to interact with us, the way to get a hold of us, or if you have a question about a technical problem, like, hey, did the screen freeze? Did I lose sound, something going on, please feel free to put those kind of questions in the chat. The other thing I'd like you to put in the chat, if you wouldn't mind, is should Amber ask you any kind of questions or seek input from you during the session, please use the chat for those kind of things. If you have a content question, so something about the material we're talking about, or some kind of question related to the meteorology event or climate, use the Q&A feature, and that's the box that's in your toolbar. It's got the question mark inside of it. We will try and do our best to get to all the questions, but I need everyone to understand a couple of things. One, we're going to have timing. We are on a limited amount of time, so we may not get to everything because of time. And also, you need to understand that by rules, there are some things that Amber can get into really in depth, and there's other stuff she's can only give you some of the basic information and tell you where you can go research some other stuff. So please understand that. And without further ado, then I will turn it over to Amber Liggett from NOAA and the Climate Program Office.
All right, thank you again, John. It's nice to see all of you. Thank you for joining in. Today we're going to be talking about the intro to the climate system. Again, some basic climate terminology and how that relates to the climate system. We're also going to go into the mechanics behind how the climate system functions, and then a bit of an overview about observations of the changing climate and evidence that the change is human caused, projections and impacts of climate change in our communities. So again, this isn't going to cover everything that you have within your rules of meteorology guide, but hoping that it will help give you some understanding there. So getting into the first piece about the climate system, we understand that Earth is the only planet that sustains life, and a number of factors are contributing to why the planet is able to be habitable. So Earth exists within the sun's zone of habitation, and with the moon, maintains a precise orbitable inclination that is needed to produce our seasons. And second, life on Earth is critically dependent on the abundance of water in all three phases, so liquid, vapor, and ice. Third, carbon is actually the basis of life on our planet. It's abundant and it's existing in all variety of forms. We're going to talk a lot about carbon. It makes up about 12% of our body's atoms, and in the atmosphere, carbon is present as part of carbon dioxide and methane, which contribute to the greenhouse effect, which is another key term that you'll hear. And that helps keep the planet's surface from being permanently frozen. And fourth, Earth's atmosphere and electromagnetic field work together to protect the planet from harmful radiation while allowing useful radiation to reach the surface and sustain life. So we're going to talk about the 6 different components of the climate system. It's a very interactive system So we have the sun, the atmosphere, our oceans, land and sea ice, the land surface, and living organisms. And the state of the climate system really does influence the chance that certain types of weather will or won't occur. And events that significantly change the climate system will change the odds of our weather outcomes. So, what we're seeing with all of the different arrows here is how all of the components are connected. And we'll get into some specifics of components, kind of starting with the atmosphere and heat energy. So, one key term here is the sun, and the sun generates all of our incoming energy to Earth's climate, and that is transferred through space to the Earth's atmosphere and surface. Now, some of this energy will warm the atmosphere and surface as heat, and that can happen either through radiation, conduction, or convection. Now, in radiation, if you've ever stood in front of a fireplace or a campfire, that would be you feeling heat transfer through radiation. So it's the transfer of heat energy through space by electromagnetic radiation, where much of the electromagnetic radiation that reaches the Earth from the sun is through visible light. And most of the solar radiation is absorbed by the atmosphere. So a lot of what we see at the Earth's surface is radiated back into the atmosphere and becomes heat energy. Now, dark colored objects such as asphalt will absorb radiant energy faster than our light colored objects. That's also why sometimes if you're wearing like dark colored clothes out in the summer, you feel a lot hotter faster. But they also radiate their energy faster than lighter colored objects. So, getting into conduction, if you've ever left a metal spoon in a pot of soup or something warm on the stove, and then after a while you come back and you touch the handle of that metal and it's really hot, that would be an example of heat transfer through conduction. So, it's the transfer of heat energy from one substance to another or within a substance. And conduction is a very effective method of heat transfer, especially in metals, but air conducts heat poorly. So we'll get into convection next, which is the transfer of heat energy in a fluid. And this is where we think of air a lot of times convection. Now, in our homes, this type of heating is most commonly seen as circulation that develops in a boiling liquid. So again, if we go back to like something boiling on the stove, you would think of boiling water. And air in the atmosphere will act as a fluid. So the sun's radiation strikes the Earth's surface and helps to warm it. And as the surface temperature rises due to conduction, heat energy is released into the atmosphere. Now, think about that forming a bubble of air, and that bubble of air is going to be warmer than its surrounding air. So, as that bubble rises into the atmosphere, it's going to cool, and heat is going to move into the surrounding atmosphere. So, this is where we're really seeing a cloud. If you think of the cloud as an air bubble, you can envision this. You can think of it as air bubble or as a hot air mass. So as this hot air mass is rising, it's replaced by surrounding cooler, more dense air, and we feel that as wind. So the differential heating really is showing us how we get our wind. And these movements of air masses can be small in a certain region, such as, again, like a small cumulus cloud, or these could be a lot larger cycles in our troposphere covering large sections of Earth. That would be a convection current, and that's responsible for weather patterns that we see in the troposphere. So taking it a step further, as I mentioned already, the sun generates all incoming energy to the Earth, but we could see in this graphic how incoming energy from the sun is balanced with outgoing energy from the Earth. So since the Earth is much cooler than the sun, its radiating energy is much weaker, infrared energy. Nonetheless, energy is absorbed at the Earth's surface, and that is balanced with the energy released from the surface. But in the center here, the atmosphere is really what plays a crucial role in this energy balance by trapping some outgoing heat through the greenhouse effect. And we're going to go into a lot more detail of the greenhouse effect right after this slide. But the atmosphere will either absorb, emit, or re-radiate energy. And so you could see from the sun, that is the atmosphere here is absorbing some of the energy. You could see in the red arrows, we have some of the energy being emitted up back to space and emitted down to the ground from the atmosphere. you also see that some of the energy is absorbed from the surface and then re-radiated or reflected back up to space from the clouds. So all of that is happening at the atmospheric level. I did want to also point out here, latent heat is energy which is stored in water vapor that is released when it's condensed. And sensible heat is a lot of what we just discussed on the previous slide with rising air via heat energy. So getting into the greenhouse effect, this refers to how certain gases in our atmosphere trap heat. So these gases would include carbon dioxide, and that causes more warming than all other human-emitted greenhouse gases combined. Also methane, nitrous oxide, and some other gases. And greenhouse gases do occur naturally, but humans are adding additional greenhouse gases into our atmosphere primarily by the burning of fossil fuels. So the initial source of heat energy or warmth is from the sun. And the sun's rays will then warm the surface of the earth, as you see in the photo here. Then we do have some of that energy being re-radiated back into the atmosphere, but some of that heat in the atmosphere, kind of at this level here and throughout, you see will actually bounce back to Earth, while some of it does escape back to space. When we only have our natural forcings, the amount of greenhouse gases ensures that heat being in the atmosphere is balanced, like we just kind of saw on the last slide, which helps keep the planet stable and warm enough to support life. But notice here, this is showing the beginning of the Industrial Revolution. As you add more greenhouse gases into the atmosphere, you're going to see more heat trapped by the atmosphere, and this throws off the balance and warming of the planet. So this, again, the beginning of the Industrial Revolution is about the 1850s when humans started burning more fossil fuels and turning forests into developed land and farms. So you can start to see a few more icons here, not just the natural, but some of these human-caused forcings. And then if you continue this on and add other activities like the flying of aircraft, for example, now we're seeing more human-enhanced greenhouse gas effect. If you think of it like piling blankets onto yourself, that's when you're starting to feel your body radiate heat onto the blanket, and then that heat radiates back onto you. That is essentially how the greenhouse gases naturally will act to warm the planet. So they catch the sun's energy, hold it close to the Earth's surface. But then if you think about it a little bit more and you put too many blankets on, you just keep piling blankets onto yourself, you're going to get uncomfortably hot. And that's what we're seeing with the human-enhanced greenhouse effect on the Earth. While carbon dioxide, again, causes more warming than all other human-emitted greenhouse gases combined, the movement of carbon from one place to another is caused by natural and human processes known as the carbon cycle. So I won't read every word here, but kind of this is where the cycle starts, is step one, and it goes all the way around here. And that's the order of the carbon cycle. So oceans have absorbed much of our carbon dioxide that people have released into the atmosphere, and that will slow the rate of warming. Also, when carbon dioxide reacts with surface water, it creates carbonic acid, which causes our ocean waters to become more acidic. And that is actually pretty harmful for our ocean life, especially corals. There's been a lot of stories that you can see right now about the bleaching of ocean corals, especially down in the Florida Gulf Coast area. And it can impact other organisms whose shells are damaged by acidic water. And I'll stop and see here with the Q&A, how do radiative transfer models compare to coupled ocean and atmosphere models, and how are they simulated? So I will say this particular question, I do not have an answer to because I do not specialize in the models. But what I would say for this particular question is that at the end, I'm going to have different links to some resources. I would look at the National Climate Assessment, and the fifth one is the most recent one out right now. I would look there because that's where they're really getting into the models and the projections. And so I'll make sure you have that link at the end. All right, moving into layers of the atmosphere. The Earth's atmosphere is primarily composed of nitrogen, making up about 78% of the atmosphere, oxygen at 21%, argon at just under 1%, so at 0.9%, and then the remaining 0.1% is trace gases, which would include some of the ones we've already discussed, like carbon dioxide, methane, and water vapor. The entire atmosphere is split into 5 different layers that we'll speak about, starting down here at the troposphere. This is the lowest level, known as the lower atmosphere. This is where mostly all weather occurs, and of course, it's where we live. Most of the water vapor in the atmosphere, along with dust and ash particles, this is really what helps to create clouds. When you have these dust and ash particles, it helps to coagulate the water droplets, and that's what makes clouds. So the troposphere begins again at the Earth's surface, but the height can actually vary, and the density of gases in the layer decreases with height, and the air will become thinner. So you kind of end the troposphere at the tropopause, and then we move into the stratosphere. So as I said, the height can vary. So the stratosphere will actually start anywhere from 4 to 12 miles above the Earth's surface and make its way up to about 31 miles into the sky. And this layer holds about 19% of the atmosphere's gases, but very little water vapor. A high concentration of ozone, which is a molecule composed of 3 atoms of oxygen, will make up this ozone layer of the stratosphere. And the ozone absorbs some of the incoming solar radiation. So when you think back about what we just talked about with the greenhouse effect, and think about ozone as being that shield of light for life on Earth and what could be potentially harmful ultraviolet light, that ozone layer is what's responsible for protecting us from that harmful radiation and also helping to regulate our temperatures. And in this region, we can actually see temperature increasing with height. That takes us to the stratopause, and then we move into the mesosphere. So that's about 31 miles to 53 miles high into the sky. And the gases here are becoming less dense with height. So temperature also is decreasing with height again in this layer. And while the troposphere is the lower atmosphere, stratosphere and mesosphere make up the middle atmosphere. That takes us to the mesopause, and then we move into the thermosphere, which goes from about 53 miles up to 375 miles. This is officially the upper atmosphere, and the air is extremely thin. The gases here in the thermosphere are increasingly dense as you decrease, going back down closer to the ground, but incoming high energy ultraviolet and X-ray radiation from the sun start to absorb, is absorbed by molecules in this layer, and that's what causes large temperature increases and also temperature increasing with height again. And then finally, the exosphere. So I'm going to switch over into this part of the image just to show you that the exosphere is the outermost layer of the atmosphere. We have atoms and molecules escaping into space. This is also where we see our satellites orbit the Earth. Also, regarding the slides, if that is something that is allowed, I'd be happy to share the slides. Okay, next we're going to talk about the Coriolis Effect. And this is important because the Earth rotates on its axis, so that circulates air, and the circulating air actually is deflected toward the right in the northern hemisphere and toward the left in the southern hemisphere, and the deflection is what's called the Coriolis effect. This is the result of the fact that different latitudes on Earth rotate at different speeds. So objects that are moving from the equator toward the poles, so kind of moving in the direction of the red arrows, is going to move into a region of slower rotational speed. So their paths are going to be deflected ahead. That's why the arrows kind of end up farther ahead of the point of origin. And then it's basically the opposite as you move from the poles toward the equator, or like high latitudes to low latitudes. That's where you're going to see deflection behind the point of origin. And this is important when we talk about winds. So the strength of the Coriolis effect is stronger near the poles and weaker near the equator. and that is what impacts the wind. We talked about differential heating with heat energy, and that differential heating of the Earth's surface results in equatorial regions receiving more heat than the poles. So essentially, as air is warmed at the equator, it becomes less dense, and less dense air is rising. So at the poles, the cold air is dense and sinking. So you kind of get a motion where we're seeing the movement go like this. And if the Earth wasn't rotating, the warm air that we have rising at the equator would reach the upper atmosphere and begin to move horizontally toward the poles. And that's kind of what we're seeing on the non-rotating Earth. The prevailing winds would basically blow from poles to the equator in both the northern and southern hemisphere. But because of that rotation of the Earth and the Coriolis effect, if we focus in first on the left image, rather than just a single atmospheric convection cell in each of our hemispheres, there's actually 3 major convection cells per hemisphere. So focusing in on these circular blue arrows, I'm going to go through those. So the convection cell, if we start near the equator here, the convection cells that are created by rising air at the equator and sinking air at 30-degree latitude, that is what's referred as the Hadley cells. And again, there's one in each hemisphere. As you move from about 30 to 60-degree latitude, you have the Ferrel cells. And then moving closer to the poles, this is between 60 and 90 degrees latitude, you have your polar cells. And then getting into the winds, when we talk about surface winds in both of these hemispheres, they're going to blow toward the equator between the 90 and 60-degree latitude mark. So like here and here. And also between 30 degrees and the equator, they're blowing towards the equator there. Now, you will see that it's actually blowing towards the poles from about 30 to 60-degree latitude. And so when we incorporate the fact that we have the Coriolis effect, that deflects the path of our winds to the right, again, in the northern hemisphere, and then to the left in the southern hemisphere. So now looking at the image here on the right and focusing in on the red arrows for the winds, now that's where we're starting to see what the actual prevailing winds look like in real life. So we have our trade winds, and those are near the equator to 30-degree latitude. And then we move into the westerlies. That's dominant between 30 and 60-degree latitude in both hemispheres. And lastly, we have the polar easterlies, which are between 60 degrees latitude and the poles. But in between, what we see here with the purple text are high pressure zones. And these occur where air is descending, while low pressure zones indicate rising air. So going back to the equator, what we see here is rising air creating a low pressure region called doldrums, or the intertropical convergence zone. And you notice that it's basically converging onto the equator here, and that's why it's called the convergence zone. And at 30-degree latitude, we have high pressure zones of descending air known as our Horse latitudes or subtropical highs. And finally, while the text isn't shown, what you would be seeing here is at 60-degree latitude, a low pressure region called the polar front. So winds kind of leads us into talking about the ocean. So while we've been mostly focusing on atmosphere, we can also talk about surface ocean currents. And these are caused by either wind, water density, and tides. And that's what you're seeing in this animation. So in the ocean, we are driven by global wind systems that are fueled by energy from the sun. We also have tidal ocean currents, and tides will create currents in the ocean near the shore, also at bays and estuaries along their coasts. So essentially, we have the rise and fall of the tides driven by gravitational attraction of the sun and the moon on the Earth's ocean. So whenever the tide is moving into the shore, we have the flood current, and when it's moving back out to sea, we have the ebb current. And this little piece of seaweed in the animation is showing you how that movement will actually go with the tidal current. We also have a thermohaline circulation, which is really important in the ocean. Thermo is coming from the word temperature, and haline is coming from the word salinity. So the deep water circulation, which is also known as the thermohaline circulation, will begin at the Earth's polar regions. So when ocean water in these areas gets very cold, we have sea ice that forms, and then the surrounding seawater is saltier, which increases in density and sinks. And so that's how we get that deep ocean current movement. And you'll see here again the arrows in just a moment. So yeah, it's getting saltier and it's moving down, and that's how we get that sink of the density. So we have, with the thermohaline circulation, we have the start of the global conveyor belt. This is a connected system of deep and surface currents that circulate across the globe on a 1,000-year time span. So the global set of ocean currents is a critical part of Earth's climate system, as well as ocean nutrient and carbon dioxide cycles. So we have warm surface currents, and the surface currents represented by the red lines, and then we have the deep ocean currents represented by the blue lines. And you could see how those will actually move throughout our oceans. So while warm surface currents carry less dense water away from the equator and toward the poles, the cold, deep ocean currents then carry that dense water away from the poles back toward the equator. You may have also heard of the Gulf Stream. This is a strong ocean current that brings warm water from the Gulf into the Atlantic Ocean. So we see that it's formed from the convergence of the North Atlantic equatorial current. And so essentially it's bringing tropical water from the east and the Florida current bringing warm water from the Gulf. And the Gulf Stream will actually take this warm water up the east coast of the US. And it's a western boundary current, meaning that the Gulf Stream experiences western intensification. So it's a very narrow current, it's deep, and it's fast. So the average speed of the Gulf Stream is nearly 4 miles per hour, and a maximum speed is about 5.5 miles per hour. And this is actually the fastest current in the ocean. It also transports a huge amount of water, which is actually, it transports more than 100 times greater than the combined flow of all the rivers on Earth. So again, this is a very fast-paced moving current. Something else you may have heard of is ENSO, or the El Nino Southern Oscillation. And this is an oscillation that really has to do with both the atmosphere and the ocean. It's a climate pattern that is affecting both the atmosphere and ocean. Under its normal conditions in the equatorial Pacific, we have the trade winds that we talked about. Those would be blowing west and moving a lot of water, warm surface water, toward the western Pacific near Southeast Asia. So as surface water would move west, it's then replaced by cold, nutrient-rich deep water through the process of upwelling, as the nutrients basically are moving up to the surface of the ocean. And so coastal upwelling will lead to a shallow thermocline in the eastern Pacific. And the thermocline is essentially the transition layer between warm mixed water at the ocean surface and cooler deep water below in the deep ocean. Now, in terms of what we're seeing in the atmosphere at this point, the trade winds are part of a convection cell called the Walker convection cell. So kind of what we see up here is talking about the Walker cell. So there's a low pressure system usually over the western Pacific when this happens, and that's going to lead to rising moist air and significant precipitation in that region. So typically a lot of rain. And in the eastern Pacific near South America, we have high pressure. It's usually pretty dry. So that's normal conditions. But then if we move into what it looks like with La Nina condition, that's when the trade winds are unusually strong. That leads to increased upwelling and transport of deep, cold ocean water to the surface. We see a lot of the effects of La Nina essentially be the opposite of El Nino. So La Nina is going to be bringing our cooler, wetter conditions to the northwestern United States and Canada, while the southeastern US receives below average precipitation. You also hear a lot about monsoon season in Asia during a La Nina and drier conditions, especially over, um, it's like monsoon season in Asia is drier during El Ninos and it's wetter during La Ninas. So essentially, like I said, opposite. And so during the last few years, we've actually been in a La Nina system. Then we've had a break in that, moved back into what we call ENSO neutral. So, like those normal conditions that we just spoke about. And currently, we are back into a very weak La Nina pattern, which is expected to only last maybe a couple more months before moving back into an ENSO neutral phase. So, then that leads us to El Nino conditions. This is where we have high pressure system over the Eastern Pacific diminish. So our trade winds are weakened. Sometimes in extreme cases, we'll actually see the trade winds completely reverse. And that's what we're seeing in this picture here. This only happens, again, in very strong cases where we have warm surface water flowing east towards South America. This will warm the coastal South American water by about 8 degrees Celsius in its strongest years. Now, when this happens, the influx of low density warm water will deepen our thermocline and prevent upwelling. So, that in itself dramatically reduces productivity of the ocean and can devastate populations of fish, other marine life, and even impact what we are seeing with fisheries.
Hey, Amber, real,
Yes.
real quick, we got LL has tossed in 2 questions here.
Okay. Let me pull it
The
up.
first one is they want to know how many months does it usually pass between La Nina and El Nino?
So it really can depend. There's no set amount of time. I will say that the patterns typically will last for each phase of INSO neutral, La Nina, El Nino. They typically will last 3 months each, but again, it's not a cycle where you know for sure after 3 months you're going into another phase. And as I said, the past couple of years we have been in the La Nina phase, and so it can last longer. And a lot of times, the different climate impacts that we've started to talk about have impacted. So, like whether we have warmer ocean waters, whether we have different air circulation patterns, things like that also impact this.
Okay. Then the other one, I think this may go back a little bit, but it was
Yeah.
asking about where does the conveyor belt start? Is there a particular ocean?
Now, that also is a good question, which I don't know that there is a particular starting point, though I do know that the deep ocean currents again would kind of start in the poles, and the surface ocean currents would start at the equator. But as far as like one exact point, I don't think that, like, I'm not aware of where that would be, but I know that since it's again that 100 or that 1,000 year cycle, it's moving so frequently that I don't know that there is like an actual starting point.
Okay. And there isn't like a kind of scientist consensus, like the assumption north is always at the top of the page kind of thing, or so we don't think of it as always in the Atlantic or always in the Pacific.
Let me see here. Just kind of looking at some of the material that we have online, just double check here if there is more of a starting point. I'm not seeing a scientific consensus on it, but I will take a look at this again after the presentation, and I can always send you a follow up if I do find that there is a starting point.
All right. So right now, LL, there's no defined starting point. So thank you very
Yeah.
much for that, Amber.
Yeah, absolutely. All right. So make sure I get back. So that's kind of where we're going to leave off on talking about a bunch of different components of the climate system. And then now we'll shift into a little more terminology, like the difference between weather and climate and what is climate change. So I'll take a pause and just ask all of you if you want to put in the chat, what is weather, if you had to define it? All right, one person says the current state of the atmosphere. I see temperature or conditions for the day, short-term event in the atmosphere. Awesome, getting a lot of answers. So the definition that we have at NOAA is that it is the current state of the atmosphere in a particular time and place. So anything that's happening outside, from the atmosphere, we could have rain, snow, sunshine, whether it's windy, all of that classifies as weather. Now, weather does not equal climate. And what I mean by that is that, in this photo, we see here a southwestern US climate. We know that that's hot and dry, but that doesn't mean you can't get a rainstorm from time to time, especially again, in certain seasons of the year. Now I'm going to ask you all, what is climate? Climate is the average of 30 years or more. That's what I see in the chat. Long-term weather conditions. I'll give it a couple more seconds. Long-term state of the atmosphere, average weather in the atmosphere for 30 years or more. All right. You guys are all correct. The long-term average of weather in a selected geography. And yes, you do need at least 30 years of data in one location to have climatology of that area. So since it is the long-term average, climate cannot be experienced firsthand like we see with weather on a daily basis. But the climate is concerned with more than just the long-term average of weather. It's also concerned with the conditions and parameters surrounding the climate system to better understand our weather outcomes. So essentially, climatologists are looking beyond that long-term 30-year average of weather to predict the long-term averages. But the state of the climate system influences the odds that certain types of weather outcomes will or won't occur. And so what we see is that humans have tilted the odds in favor of a warmer atmosphere, warmer temperatures, and this is an image where we can really see that. And this is from the 5th National Climate Assessment, which came out in 2023. So showing observed changes in annual winter and summer temperature. And the big kind of takeaway here is that if we were in a stable climate, you would roughly see equal outcomes over time in terms of warm and cold temperature records. And so, of course, we do still see cold temperature records being set and cold spells like we had in much of the eastern US earlier this month, for example, but there's really no comparison to what we're seeing on the warm temperature record trend, for example, 2024 being the nation's warmest year on record. Some other terms to differentiate are climate change and global warming. And so this isn't a typical Venn diagram. You notice global warming is within it, and that's because the terms are related. And what matters when you talk about them is the geographical scale, the time period, and the variable. So both occur, both can be natural, but both can also be human caused. Now, humans are modifying the climate system such that extremes are more frequent and more severe. So when we talk about climate change, what we're saying is the change in the long-term average of weather patterns across multiple parts of the climate system, where impacts can be, anything from humidity, cloudiness, wind, or even rain. These impacts would be local, regional, continental, like the entire North American continent, or even global in scale. That's climate change. While global warming is referring to one variable, so in this case, temperature, moving in one direction, only warming, and on one scale being global. So this can have resultant climatic changes, and warming can cause places to dry or become wetter, and it could change circulation patterns that cause more humidity or more cloudiness. But global warming is a subset of climate change. That's like the key takeaway on this slide. If the globe is warming, there will inevitably be resultant climatic changes, but those will happen at different rates and different degrees of magnitudes depending on where you're physically located. Another important term is climate variability, and I have a couple images here talking a little bit more about El Nino and La Nina. So climate variability itself alters the average of weather patterns due to natural causes on relatively short to medium time spans. So climate variability is natural. It's going to happen with or without global warming. And these patterns are occurring in a greenhouse gas enhanced atmosphere now, which means that the patterns may produce extreme events. And this is kind of what I was talking about with my answer to the question about, how long do they typically last, like the phases of ENSO. It really does depend now that we have more climate change and more enhanced impacts from humans, where we can end up with these extreme scenarios, extreme phases of ENSO. Now, climate scientists do understand oscillating patterns and mechanisms. When we talk about the fact that ENSO is a natural climate variability pattern, I also want to point out that it's not the only pattern. There's a whole family of oscillations in the climate system that are naturally occurring. These are natural phenomena that happen with or without global warming. They're all under the umbrella of climate change and kind of tilt the odds in favor of or against certain weather phenomena like droughts, extreme rain, floods. So all of those work together. So moving into the climate mechanics, this is where we're going to talk about why and how the Earth warms and cools and how today's warming will differ from past warming periods. Essentially, we'll see that Earth's temperature has fluctuated dramatically in the past, and there's some long-term trends that we'll take a look at, and you can see why scientists are more concerned with the warming that we have today. So today's warming is, again, being driven by more human buildup at a faster rate. It's about 50 to 100 times faster than what it took Mother Nature to do using our natural climate changes. And so when we look back about 10 to 12,000 years ago, we could see the changes. So getting into some of the information there, what causes our climate system to change is a term called forcings, which is, again, a driver of climate change. Some examples would include volcanoes and changes in the sun and ocean currents. These are things that have impacted the climate since long before humans were here. One really good example is how Earth's orbit has changed on a 100,000 year cycle. This changes how much sun the Earth gets, and that creates ice ages. So when we think back on ice ages, it actually takes the Earth over 10,000 years to warm back up after each ice age. And with our current climate change and the fact that that's adding human-caused forcings, primarily heat-trapping gases like carbon dioxide from the burning of fossil fuels on top of these existing natural forcing cycles, is causing the rate of global warming to increase far faster than life on Earth is used to. So essentially kind of tipping the scale of the climate system in favor of more extreme weather events is what we've been seeing. We can also compare the term forcing with feedbacks. So a forcing is anything that triggers the change in the climate system. So again, if the sun intensified, that would force our globe to warm more, and vice versa if the sun was less intense. And the main forcing that we have, again, is greenhouse gases in our atmosphere. But then when we talk about feedbacks, these are essentially consequences of climate forcings. So every forcing has a sort of climate feedback. And feedbacks can happen in loops. Feedback loops can be both positive or negative. So an example of positive feedback loop is amplifying a warming trend, and a negative feedback loop would be dampening it. So again, like that opposite, equal and opposite effect. Now, what I'm showing you here is an example of a positive feedback loop with melting permafrost in an Arctic region. And permafrost is essentially ground that has been frozen for at least 2 years. And this picture is showing a chunk of that frozen ground has actually broken off from its mainland and into the ocean in the Arctic. And so over geologic time, we've seen that the Arctic region has become a sink, a carbon sink, drawing carbon out of the atmosphere due to photosynthesis. And we have a buildup of that carbon in the soil, which becomes plant matter, and that's why it's called fossil fuels. Well, if we dig that back up and put it back into the atmosphere, that's when we begin to see that permafrost thawing out. Now, that is normal to have permafrost thaw a bit, but what's not normal is that it's staying thawed a lot longer throughout the year as we are having more warming. And the soil starts to decompose, and that in itself releases more heat trapping gases with the carbon dioxide and methane into the atmosphere. So we have more greenhouse gases further warming the atmosphere, promoting more warming, more melting of the ice, more warming, and so forth. So that's how you get that feedback loop. It's amplifying the effect of the driver. And our ability to predict something like melting permafrost is somewhat limited, but it's going to be a big feedback loop that you're going to hear be talked about a lot more in the future. And the outgassing of these greenhouse gases from permafrost is occurring, especially in Alaska, Canada, Northern Europe, and Asia. So again, these are the areas that we're going to be continuing to see scientists review and study. I will say too, an example of a negative feedback loop is if we had increased cloud cover, and that would help reflect more sunlight back to space. So basically, you'd have that incoming solar radiation hit the cloud and re-radiate back to space. That would reduce the amount of solar radiation that's actually been absorbed by the Earth's surface, which can lead to a cooling effect and counteract some warming. And the same thing happens just in general on a smaller scale. On a cloudy day, you actually are going to have cooler temperatures on the ground on a cloudy day versus a clear day where you're getting all of that incoming solar radiation hitting the ground a lot more. Now, Earth's temperature is not too hot or too cold. It's actually just right for humanity, and that is why it's called the Goldilocks Planet. But does anyone have a guess, if you want to put in the chat, what the globally average annual temperature is in degrees Fahrenheit? I'll give it just a couple moments. "85" is one guess. 61, let's see, 75, 60 degrees. All right. The answer is 59 degrees. So the person who said 60 degrees was definitely the closest. And yeah, that's the globally average annual temperature is 59 degrees Fahrenheit. But carbon dioxide will warm the atmosphere enough to hold water vapor, and water vapor will keep the Earth warm. So without carbon dioxide, the Earth's greenhouse effect would collapse. But with more atmospheric water vapor, that traps more heat near the surface, causing global warming. Now, a warmer atmosphere is a thirstier atmosphere. So for every degree Fahrenheit that the atmosphere warms, it can hold 4% more water vapor. And similarly with the ocean, a warmer ocean will evaporate more water readily. So all of this increased water in the atmosphere impacts the climate system. And the way we see that is through stronger storms and more intense storms. So when we're talking about hurricanes, when we're talking about rain and snow events, we're seeing a lot stronger of these systems because there's a lot more water vapor in the atmosphere. And one more question for all of you. If you've ever heard of the term tipping point, how would you define it? And I'll just give it a couple of moments here. And these would be tipping points across the climate system. And remembering that we've already seen this image here with permafrost before. Okay, I'm not seeing any guesses, and that is okay. I will go ahead. Oh, I see one. I see a couple. The temperature in which the ecosystem fails. Oh, wait, I think that was related to the other part. A point where something can't stand anything more and it goes bad. Okay, that's a good guess. Essentially, tipping points are the culmination of small changes in the climate system that add up over time and result in large-scale, high-impact cascading changes. These are irreversible, and that could be for tens of thousands or millions of years. So for our purposes, like not in our lifetime. And current climate trajectories are causing concern that we might start to hit or have already tipped some of these points. And going back to permafrost, we already said that that's an example of a positive feedback loop. It's also an example of a tipping point. And so I do have one more section, but what I think I'll do is stop here to take some more questions, and I'll make sure that you all get this last section in the slide deck when I send that out. So I'll take a pause and see if there's any specific questions on anything else that I've covered. And if not, I'll continue on.
Great. Any questions for Amber, guys? This is the time to shoot them out. We got about 8 minutes or so left. So now's the time to get questions answered. Okay. This one just dropped in the chat.
Okay.
Ramakrishna is asking about what are the RCP values?
So RCP, these are representative concentration pathways. That's what RCP stands for. When we are talking about climate models and projecting what the future is going to look like for climate change, those are RCPs. You're seeing typically a low emission scenario or a higher emission scenario. So I'll just fast forward here to show you something where I think you can see this better. So this blue section here is a low emission scenario, and this red section is a high emission scenario. And this specifically is referring to high tide flooding. And when we look at RCP as being low emission scenario, that could be like around 2.6 RCP. Intermediate emission scenario might be like 4.5 RCP, and high emission scenario would be like 8.5. And so essentially what I'm getting at in this slide here is the fact that high tide flooding days are changing. So like right now in Boston, there's around 9 high tide flooding days. And by 2050, you would be at 60 days in 2050 and 200 days in 2100, which would only be in that low emission scenario. Whereas in the high emission scenario, which would be a worser case where we don't take as many efforts to reverse climate change and reduce our greenhouse gas emissions and things like that, that's where we would actually see like a higher number. So 70 days in 2050 and 350 days of high tide flooding in 2100 under a high emission scenario, for example.
All right.
Let's see, there's any others.
Anything else?
Okay, well, I might just go back, and while I said I went a little ahead, just kind of go back to the start of this section here. So a question of why the Earth is warming so rapidly now, and the fact that we've talked a lot about how hot it is with global warming and the climate change that we're seeing. We are experiencing the warmest multi-century period in 100,000 years that we've experienced, with the fastest rate of warming in at least the last 2,000 years. So this combination of speed and magnitude of change in temperature is unprecedented. And we could say that it's unprecedented even in the last 4 million years. And over the next century, we are projecting that the rate of warming will be about 10 times faster than it was for the past 65 million years. So these are very large time frames that we're talking about. This isn't 100 years or 200 years. So essentially the takeaway here is that while the climate has changed in the past, it was a lot slower than what we're seeing since the Industrial Revolution. We're seeing that the changes have been on a much faster rate. And when we think about how much energy it took to warm the Earth out of the last ice age, the answer is actually about 1 watt per square meter, give or take 4/10 of a watt per square meter. And that's equivalent to the energy that's in one Christmas light bulb. And by comparison, really for every 3 foot by 3 foot patch of surface area, we saw that Mother Nature was forcing of this 1 watt per square meter, whereas humans are actually doing a sustained forcing of 3 watt per square meter, meaning that we've already surpassed this average natural amount by 3 times. And that's one thing that we're seeing with energy and how much it took to warm out of the last ice age versus the energy that we're emitting now. And quickly going into a little bit about the history of carbon dioxide and the fluctuations over the past 800,000 years. This is including the ice ages and interglacial periods, which I briefly mentioned before. But again, we're seeing a dramatic increase in the amount of carbon dioxide that's emitted right now. And ppm is parts per million. So as of December of last year, so like a month ago, we were at 425 ppm, whereas the previous highest was 300 ppm. That was, that was about 300,000 years ago. So we're seeing again this dramatic increase in carbon dioxide values. And carbon dioxide and temperature, we know that while carbon dioxide acts as a thermostat for Earth and increases in carbon dioxide over the last 150 years has been driving global warming, essentially from 1880 to present, that's where we have a lot of our data from. That's where people are looking at proxy data and being able to make projections into the future based on from this point back in history. And these red and blue bars that we see here are showing differences in temperature from the average temperature in the 20th century and really showing us how it is getting hotter every decade, as well as the magnitude of change in temperature is exactly matching the global concentration of carbon dioxide on this right axis. So this takeaway on this slide is that carbon dioxide is driving global warming. And where we're at with numbers right now is that many areas of the world, a record average temperature has been measured by humans for over a century. And in other places, the data set doesn't stretch back that far, but often, again, we're using these natural proxies like the trees and tree cores, sediment that we have from oceans and lakes, as well as coral reefs. We're using all of those kinds of natural proxies to determine the conditions of a particular time and place. And all of these proxy data are serving as records of temperature and greenhouse gas concentrations going back thousands of years. And lastly, we are seeing that the Earth's average temperature has increased by about 1 degree Celsius or 1.8 degrees Fahrenheit back since that Industrial Revolution started in 1880. So these are some of the current numbers where we're at. And I'll just skip over to the end to go over a couple of additional resources that I think would be really helpful as you continue to do your studies here. So climate.gov, my office actually oversees climate.gov as well as the US Climate Resilience Toolkit. But focusing in on climate.gov, there is an entire section called Teaching Climate, and there's free resources there. There's experiments, there's just like good reading on that as well to learn a little bit more about climate summaries and regional and national resources about climate change. It also has the climate literacy guide, which I would encourage all of you to take a look at. There is a new one that just came out at the end of 2024 called Climate Literacy Essential Principles for Understanding and Addressing Climate Change. You can find that here at climate.gov. As I said, the US Climate Resilience Toolkit is something else that our office is maintaining, and this really has tools and case studies to help people understand how to adapt to changing climate, how to build resilience to changing climate. So this could be helpful just to get a better understanding. I already mentioned too the 5th National Climate Assessment. This would be the link for that. This has information really summarizing information on climate change across the United States, but it also breaks it down into regions and cross-sector topics and goes into a lot of great detail. There's a lot of visuals in there as well. And then lastly, there's different reports through this Intergovernmental Panel on Climate Change. They have some summaries, like example, summary for policymakers that break down a lot of plain language explanations of more of the global climate change impacts that we're seeing. And so this would be that link. So I wanted to leave those for you all. And could I review methane and water vapor impacts? So trying to make sure I fully understand the question when you say impacts. So basically with methane and water vapor, really what we're seeing is that, again, those are contributing to the greenhouse gases, that the human enhanced greenhouse gases. So I would say what the biggest impacts that we're seeing with that are going to be the global warming, the more extreme events. And if you, I don't know if you could specify a little bit more of the question.
Hey, Amber,
But yeah,
they may be getting at the idea of, is one worse than the other? Is one, or, you know, or does one
okay.
have a bigger effect than the other one?
Yeah, so carbon dioxide would be the one that has the biggest effect out of like water vapor, methane, and other gases. Carbon dioxide is the one that has been causing most of the warming. We've had more carbon dioxide. We also have had a lot of methane that is in the atmosphere as well. But yeah, that's what I would say is the most powerful gas. The most, I would say the most impactful, not necessarily powerful, but the most impactful gas that we are having that we're seeing a lot of the impacts to the climate be from is, again, carbon dioxide. And there are some more resources on those, like more details on the different sources here, especially at climate.gov. There's a lot of information. I put a page together about greenhouse gases specifically. If you go to climate.gov/GHG, there's a lot of resources there.
All right. Thank you very much, Amber. To the question, will you guys get the slides? Yes, Amber said she would be willing to share the slides. So we'll make sure they get posted and available to everybody. But if you guys could thank her so much for presenting tonight. I always love it when you guys talk because there's like cool things I learn, and I gotta say, I mean, some of the graphics you get Noah's produced, and you know, I mean, you gotta go to the source. You guys have some fantastic, really understandable graphics. So thank you for sharing that, and thank you for sharing the resources.
Absolutely. And I am going to follow up on the question of where does the global conveyor belt start? So I will make sure to send that to John.
Awesome. Thank you very much. And I'll make sure we get that posted up on the Science Olympiad website so everybody knows.
All right, sounds
Otherwise,
great.
thank you again so much and have a wonderful evening, everybody.